Yeah, I'll be talking about Python syntax features and what it is we do when we have new syntax and we need to implement it. And hopefully this will be a fun journey through the Python compiler. I'll try to make everything as understandable as possible, but if anyone has any questions, just shout out your questions. It's totally fine to interrupt me as well. A little bit about myself. I work for a company called Quantsite Labs. I do open source for my day job. I'm working on Python, on CPython, on NumPy. I'm also doing some other ecosystem stuff. And lately, and the most exciting thing I've been working on is organizing PyCon Greece. It's the first edition of the conference. We're really excited. I see some familiar faces who are organizers as well, so come talk to us. And come to Greece, it's going to be amazing. But today I'm going to be talking about Python 3.14. It's a big release. It's bigger in terms of changes, I think, than the previous ones. Okay, free threading, yeah. But it's got a lot of release highlights in the What's New document. But we're only focusing on one of those changes today, and that's PEP 750, template strings, or what we call them, T-strings. So I'm going to go through what a T-string is very, very quickly. That's not what this talk is about. But if you want to talk more about T-strings, come find me after, and we can chat about them. T-strings are this string-looking thing that starts with a T prefix that's not really a string. T-strings are actually another type, a template type, which gives you access to the static parts of the string, or what would be an F string, and the interpolation parts of the string. So, for example, in this case, T hello world, we only have static parts, so only the strings tuple is populated, interpolations is empty. But what happens in case we have something like this? We get access to the static part, the hello, but we also get access to an interpolation object, which gives us the value of the variable we're interpolating, or any expression for that matter. A question one might have is, okay, what good does that do me? How can I use that? And the answer is you can write wrapper functions around templates to get access to those string parts and do some basic processing. For example, if you see this thing, Prague is lowercase, but we can write a function that quickly goes through all of the interpolations and capitalizes them. And then we can use that and get Prague uppercase. Enough about T-strings, though. You came here to hear more about the implementation. So yeah, that's what I'm going to be talking about today. And like I said at the beginning, this is going to be a journey through the different steps the compiler takes to take your source code and actually get to the resulting thing of that source code, of running that source code. So yeah, hopefully this will be fun. Before we actually dive into that, I want to talk very quickly about different Pythons that there are out there. There's not only CPython, which is the Python most of us use. There's also a lot of other different implementations, like Jython, IronPython, PyPy. But the stuff I'm going to be talking about today are very specific to CPython. For most of the cases, all of these have exactly the same or very similar syntax, but the way they approach parsing or tokenizing or stuff like that is fairly different. So what I'm going to be talking about today is mainly focused on CPython. Okay, syntax. What is syntax? And mainly, what are syntactic changes? We're talking about implementing syntax changes. What are these? So examples of syntax changes are T-strings, the new type parameter syntax, except star, structural pattern matching is basically any change in the language that you can use using a new piece of syntax. For example, the T prefix was not there before, It's there now, so that constitutes something new that the compiler has to learn how to handle. Not all changes are syntax changes. Free threading is not a syntax change, right? There's no new syntax you can use to implement something in the free threaded mode. The JIT has no new syntax. The per interpreter GIL or multiple interpreters, there are those kinds of changes that are different, that make a difference to how the interpreter works internally, but those changes are not exposed to the user as syntax. We're going to be talking about all the different steps, and the steps are mainly 4. When the compiler starts, it does, the tokenizer takes over and tokenizes the source code. Then we got the parser to the bytecode compiler, and finally to the interpreter. This is going to be a very high-level view, so I'm not going into the nitty-gritty details for like the JIT or the Tier 2 optimizer or things that may be happening between those. I'm just going to give a high-level overview. So the tokenizer takes source code and produces tokens. Tokens are basically meaningful units of syntax that do not take into account things like white space or stuff that's not really relevant to running the code, just there as cosmetic formatting, basically. What the tokenizer does is breaks down. So takes source code, breaks down into tokens. When we have this example, what the tokenizer will do is it has 2 internal pointers. Actually, it has loads of internal pointers, but 2 are the most important ones that basically read the input and do something like this. So, for example, the tokenizer goes character by character, and every time it actually knows where to cut that input. So for example, here, it goes to the H, it knows that it's already seen a new token, so what it does is it emits a new token with a name t-string start. And it does that continually until it has produced tokens for all of the source code it has to analyze. So the next step is, for example, hello. This is, yes, there you go. Hello. This is a token we call t-string middle. And then it goes into another mode where when it sees a brace, then it knows, okay, what do we have, what we had up until now was like the static part of the string. Now we need to go into tokenizing actual Python syntax. So it produces a brace, then the value is a name token, that's what we call it, then another brace token, and then it goes back to the string tokenizing mode and sees a code and does a t-string add. So, so tokenizing, the input we had actually produces these 6 tokens. And the changes that we need to do to the tokenizer is basically write code to correctly recognize the new tokens. This is a fairly complicated piece of code that's been there for basically ever. It's also it's generally easier said than done. Okay, that's what I'm going to say. It has to do a lot with pointer manipulation because we have those pointers and we have to keep track of what they do. So yeah, it's a tedious thing to write new syntax in the tokenizer. It's not the same when it comes to the parser. That's much easier. Why? We're going to see later. But for now, the parser takes those tokens as input and it produces an abstract syntax tree. It analyzes that stream of tokens. It generally checks to see whether that stream of tokens is actually valid Python syntax. And then if it is, it produces a tree-like data structure that's easier for the compiler to process later. So the first thing it does is it checks to see whether the syntax conforms to a formal grammar. But what is a formal grammar? A formal grammar is a set of rules written somewhat like this that basically describe the whole syntax of Python. For example, a t-string is nothing more than just a t-string start token, a t-string end token at the end, and something called a t-string middle in the middle. And you can see that t-string middle is actually lowercase, which is basically a reference to another rule. So when we get to t-string middle, we'll need to jump to another rule that is going to tell us what tokens the parser needs to see in order for the syntax to be valid in that middle part. So it starts from left to right and does a scan of all the tokens and checks to see whether the token is correct. For example, t-string start is correct, so it says, okay, let's go to the next one. It goes to t-string middle, but that's a reference to another rule, so it goes to that other rule, and it sees t-string replacement field. And t-string replacement field is a very fancy way of saying that thing between the braces. So that is yet another rule, so it goes up to that rule and sees that the first token there needs to be a left brace. So it checks to see whether the next token is a left brace. It's not, so it fails. That rule fails and goes up the stack to the rule that was in the stack before. And every time a rule fails, that's in an alternative in the parent rule, those alternatives are run in order. So because t-string replacement field failed here, we'll go to the next alternative and we'll check whether that one is correct. And that gives us the ability to say that, for example, an expression can be one thing or that other thing. For example, an expression can be a star followed by a name, and that's a start expression, or it could be a name by itself, and that's a name that's evaluated by itself. So alternatives give us the ability to formalize syntax and formalize that one thing can actually be many different things. So the second alternative is run here, and t-string middle is the next token that the parser needs to see, and that's actually it. So t-string middle is correctly matched. And then it goes back to the parent rule. T-string middle has succeeded, but because it has succeeded, and the star there means that I need 0 or more of them. So it continually calls the rule until it has failed. So in this case, we'll go back into it. We'll go into t-string replacement field. We'll see an L brace, which is correct. We'll go into a rule called annotated right-hand side, which is arguably not the best name. But that's basically a rule that defines what an expression is. And trust me when I say that it actually matches a name token, but we'll not go into that. Then it goes into things that are optional. So the things between the brackets are optional. So even if our brace is not matched correctly, it does not fail the rule because it is optional. It goes to the next token, still not it. It goes into the next optional thing, still not it, and then goes to the R brace where it matches correctly. And then the whole thing continues. We go back into t-string middle because we just succeeded, so we need to go back to check whether there's another thing in the sequence. That fails, so we go to t-string end, and yeah, it's matched all the right tokens. But I said before that it checks and then it generates, and that's why the actual grammar looks something like this, because it has to do a lot of different things. And the t-string rule is actually this thing over here. And it's got a lot more information than what I showed you before, because this rule is used to generate C code to actually do the parsing. So it's got things like types, it's got things like flags, and this flag in specific specifies that the result of this rule needs to be memoized, so needs to be able to be reused in case it's seen again in the same position. It's got things like variable assignment, so that we can use those variables in the code that will execute. And it's got things like functions, like actions. And those actions are run in case the alternative succeeds. And this is the function that constructs the AST. I told you before that there is AST construction to be made, so let's see what the parser does. It creates a template string node. It has two values. It has one constant that has the hello value. Remember that our t-string was hello and then in braces value. It has an interpolation, a name, which is value, and then a string, which is value. Notice how the interpolation part has value twice. That's once for the actual variable and once for the text that's inside the braces. We need that to do some further processing further down the road. So this is that tree-like syntax structure that the compiler actually uses. So in order to change the parser when new syntax arrives, we just need to write grammar rules. We actually, most of the time, don't need to touch any code. It's just writing those grammar rules to understand that new syntax. The only thing that we need to write in terms of code is how to generate the AST in case that, those new rules succeed. It's fairly easy, and that's because of the grammar generator. Grammar generators are generally really nice and generate code. I mean, our grammar generator is fairly simple, but there's very, very complicated grammar generators out there, and it really simplifies the process of writing new syntax rules. One thing that I didn't mention is that we have those kind of invalid rules. Those are rules that actually raise specific error messages in syntax errors. So, for example, if we do something like this, you'll actually get a nice looking error and the caret will show to the correct position. So we do that in different ways. One of the ways is define that in the grammar itself. We're going to the next part, the bytecode compiler, which takes that tree-like structure and actually emits bytecode that the Python VM can understand. Bytecodes, in case you were here before and some of the previous talk about the JIT or about CPython, bytecode is those sort of units of work that the interpreter needs to do in order to run your code. It's basically similar to machine code, but it's not a CPU that understands it. It's the Python virtual machine that understands that bytecode. So the compiler does compilation, and it takes that tree-like structure and emits bytecode. So it goes to the structure, it sees a constant, and a constant actually is a load const instruction. Hello will be the argument to that load const. When it sees an interpolation, it goes, it actually does two passes. That's why I'm going up again. And at first, it only checks the constant nodes, right? And the constant nodes, we need that, empty string for some further processing down the line, but it's not really important why. And then it goes through the interpolation. It sees the name. A name corresponds to a load name instruction. Value is going to be the argument to that load name instruction, and then goes further. It does a load const again, because load const is actually loading a constant. So in this case, a string, a static string. Load name is going and fetching the value of the variable with that name from the symbol table and actually loading that value of the variable. So it's then done with the interpolation. We built an interpolation object. We'll see what all of this means. And then template stir is a build tuple and a build template instruction. So that tree data structure gets transformed into a series of bytecodes that are fairly small units of work that the interpreter has to do in order to take your t-string and actually transform it into the template object you'll get when you evaluate a t-string. The compiler also does some optimizations here. For example, if you see the three first instruction, that's always a constant. So instead of doing 2 load consts and a build tuple, it actually does a load const of the tuple itself, because it's always the same tuple, so it knows to optimize that. I'm not gonna go into further optimizations. There's some stuff that's done here, but this is a good high-level overview of what the bytecode for a t-string will look like. So when we're having new syntax, we're changing the bytecode compiler. It's sometimes challenging, and that's, again, because it's handwritten code. We have to go into the code itself and write, explicitly write C code that implements those new rules that we have, that when you see that node in the abstract syntax tree, emit that bytecode, and yeah, that's it. So yeah, sometimes challenging. And the final part of the puzzle is the interpreter. The interpreter gets that bytecode, the series of instructions we emitted earlier, and evaluates those. The CPython interpreter is a stack-based interpreter, so it has a stack where it keeps all of the relevant values that it's going to need in order to evaluate your code. So it does the evaluation in the following manner. We have that stack I mentioned before, and it goes through the bytecodes line by line and basically executes them. This is a very, very high-level overview of what it does, but it basically does this. So the first thing it does is it loads a const onto the stack, so that item goes onto the stack. Next thing is it loads a name onto the stack, so it goes and checks what the value of that variable value is and loads that onto the stack. The next thing is it loads a value onto the stack. I'm sorry, not a value. It loads a constant onto the stack with the value string containing the string value. It then builds an interpolation, and what that instruction does is basically creating an interpolation type and packing into that type those 2 topmost parts of the stack. That's why the 2 there, that's the argument to the build interpolation instruction, which says take the 2 topmost elements from the stack, pack them into a type, and then what the VM does is pushes that interpolation object back onto the stack. It then evaluates that build tuple instruction. So it creates an 1-element tuple with the interpolation in it. It pushes that onto the stack once again, and then it builds a template. So what a build template does is takes 2 elements from the stack. That's going to be the strings and the interpolation tuples we see now, and we know how they have been created, and it creates a type and packs them into that template type. It's basically an implementation detail, but strings always has an empty string at the beginning or the end in case the t-string begins or ends with an interpolation. So basically, the t-string can be recreated in case you take all of the strings and pack the interpolation between them. So yeah, we've gone full circle basically, and from this element comes what we had in the very, very beginning. So we've seen how CPython does that job, and in order to change the interpreter, so in order to change what happens when evaluating that bytecode, is we need to write bytecode definitions. So for these new definitions we had, the new instructions were build interpolation and build template. So we have to go into the interpreter and write what the interpreter will do when seeing those new bytecodes. And because of a DSL, that's easier than it sounds. DSLs, or the DSL we have for the CPython VM is really nice, and it makes the job of writing new bytecode definitions much, much easier than it would be otherwise. And so, yeah, that's all of it, basically. Like I said, we have 4 parts to evaluating a piece of Python syntax. We have the initial source code. The tokenizer creates a stream of tokens. The parser takes those tokens and emits an abstract syntax tree. The bytecode compiler takes that abstract syntax tree and emits bytecode, and the bytecode gets then evaluated by the interpreter, which gives us the final result. That's it. This is the end of our journey, and yeah, I'll take some questions.
All right, if people have questions, there are microphones set up here. Yeah, please. Hold on a second.
Oh, okay.
Okay, I think it's now working.
Hi, thanks for your nice talk. Maybe I have a bit of a silly question, maybe it's my understanding, but when we're parsing the T string, we're assigning the T and then the apostrophe, the double quote, into the T string start token. Next, in the next step, we're, in the first step we're tokenizing it in this way, and in the second step we're parsing it, but it feels like we're validating that this T string is starting with the T double quote. Are there cases where it doesn't? It feels like we're doing things twice to me, but. So
that's a good observation. The reason we do this is because in Python we have many different forms of strings, and an F string and a T string are tokenized differently than a string without an F or a T. And because normal strings are string tokens, so the whole string is a string, we need a new token type in order to differentiate between a string, a T string, and an F string. And so we tokenize that differently, and then in the parser check to see which one of the cases we are in.
Okay. Yeah. Thanks for your answer.
Sure.
Any other questions? Yeah, please.
Yeah, when you were generating the bytecode, you went down the left and you got the hello, and you went down the right and got the empty quote. I didn't really understand where the empty quote came from.
Which part are you talking about? Is it here when evaluating or when generating the bytecode?
So the tuple where you have hello and the quote, I meant that second quote.
Yeah.
Where did that come from?
Oh, that comes from the bytecode compiler itself. The bytecode compiler itself has some logic baked into it that knows that when the last part of a T string is an interpolation, add another load const onto the stack, into the bytecode stream, so that the correct thing gets then packed into the template type. So this is logic actually written inside the compiler.
Okay. But you mentioned that it could also have a quote before.
Yeah,
is that right?
That's correct. Yeah. So if the compiler says that the T string starts with an interpolation, it adds a load const at the very beginning as well.
All right. Thanks.
Okay, we have time for one more question, I think. Maybe two, if you talk fast. Yeah.
Out of curiosity, where the different Python's implementation diverge? Like, is in the interpreter, or in the AST, on the tokenizer? Can you talk about it a little?
I don't really know the exact details. I know that the interpreter is different for most of the implementations. I'm not actually 100% sure how they implement the parser, because in CPython in 3.9 we changed the parser and we implemented a PEG, and I am not actually 100% sure whether the other implementations have done that switch as well or not. But this is basic stuff that's done the same for a lot of the programming languages out there. It's just the details that change of how we do it.
All right, one last question, quickly.
Okay, I have a question about the end of the T string. So how does the tokenizer know that this quotation mark is the end of the T string, not any other string? That's
a good question. What the tokenizer does, it has internal state, And every time it enters a new string, it basically, it keeps a stack of modes, let's say, okay? So the first mode it uses is the normal Python syntax mode. When it enters, it emits a t-string start, it goes into what we call t-string mode, and then it knows how to tokenize a t-string. And then if it enters into an f-string start, it goes into f-string mode. And when it sees the last token, where it knows that the string now needs to end, it sees whether it's in t-string mode or in f-string mode, and it knows to emit that specific token.
All right, let's have another round of applause for Lysandros. Thanks, everyone.
Come to Greece.